paths that we'll talk about, and that's sort of a general kind of thing that can be used to understand functions of more than one variable. We will review gradient vectors and talk about something called the gradient vector field, which essentially is plotting a bunch of gradient vectors all at once. And we'll talk about how to think about functions whose domain is the plane, R2, and whose codomain is the real number line. How to think about those functions in terms of polar coordinates and something called the Generalized Chain Rule. We will not be able to fully explain that. We won't have time for that, but we'll start that at the end of class today. So let's start with the chain rule for paths. What's that about? So here's the function we've been working with. When I entered this function before, I entered it without the curly braces around the x, y. In other words, I treated the function as having two separate inputs, x and y, and you can plug in values for x and y separately. However, if I'm going to do what I'm going to do in this particular animation I ultimately make, and that's going to be to draw some vectors in here, I'm ultimately going to want to think of the input as a list. In Mathematica, you use the curly braces and separate the inputs by a comma. That's one quantity called a list in Mathematica. Or mathematically speaking, in thinking about it as a point or a vector, I'm going to want to enter the same function like this. Okay? And it does do the same thing. It just thinks of the inputs in different ways. So f of 2, 3 can be evaluated that way. Well, actually, that worked without the curly braces, but there are going to be other things that we do that do require the curly braces. When you evaluate the function at particular numbers, evidently it doesn't matter. What have we done with this? We've graphed the three-dimensional plot. We can also graph the contour map with ContourPlot. Here's the syntax. I don't think I need the curly braces there. I think it's okay. We are going to need them in another spot, though, so it's worth having them there in the definition. So I can make a contour plot. Here's the basic contour plot that we've seen before already. Let's add some more contours in, like 50 of them instead. And again, recall the meaning. These are the lower curves for that function. Along these curves, the function is constant. You can find the value of that constant by moving the cursor over the lower curves. So the output of the function along this particular curve is 253. Notice, I really haven't focused on this before, but notice that these lower curves are not always equally spaced. They change their spacing. However, there's something called the contour interval for this particular contour plot that was discussed in at the beginning of chapter 14, I believe. That does stay constant. If you see the difference in the outputs between successive level curves, for example, if I go from this one, whose output is 253, to the one next to it that's toward the lighter shading, the output's going to be higher. How much higher? 4.6 units higher. 253, look at this number here, plus 4.6 is 257.6. And that 4.6 stays constant. If I go to the next curve, the value of the function will be 4.6 greater than 257.6. It'll be up to, what, 262.2? Yes. Then it goes up 4.6 again. That'll be up to 266.8. Yes. Okay, so every time you go to the next level curve that's pictured here, the value of the function goes up by 4.6. That's called the contour interval, and that's constant. And that helps give meaning to the distance between these curves. You can see they're pretty close down there. That means, three-dimensionally speaking, and you thought about this for the graded assignment, that the graph is going to go up pretty rapidly as you move this way. If you imagine the three-dimensional graph, which again in this picture would be, imagine the z-axis coming out of the screen and the graph being in front of the screen. The value of the function goes up very rapidly when the level curves are close together, more slowly when they're further apart. The graph is flatter, so to speak, in this region here near the origin when the curves are further apart. All right, let's add in a particular parametric curve here. And what I'm going to pick is kind of interesting. It's got kind of it does a loop-the-loop. I'm going to make the x-coordinate be t squared minus 1 and the y-coordinate be t cubed minus t. I need to combine it with the contour plot through show. I'm going to use ParametricPlot. We are ultimately going to animate this, so I'm going to put this in a manipulate as well. But let's get the R of t in here. T is going to go from 0 to, actually we're going to go from -2 up to b, where b is going to be the animation parameter. So now I embed this in a manipulate. Need my animation parameter, the range of values to be right here. I'll start at -1.999 and go up to +2. So this should make an animation of the curve. Well, let's see.
I'm going to type in B.
All right, we can see the quality maybe is not going to be as nice as we might like. If we play this. Yeah, that's not so good. Of course, we can fix that. I've shown you how to do that before. Performance goal. I don't think I've shown you this before, but if you notice that if you start typing some command, you see different options there. If you click on this, it'll finish it for you. It also puts an arrow in there automatically. And then it also gives you two options, speed or quality. We'll go for quality. Now it stays smoother, although computationally speaking, it goes a bit slower, and so it might be a little bit jerky over the path itself. Yeah, kind of jerky, but that's okay. Let's make that easier to see as well. All right, so this is a path. This is a path going through this plane, this XY plane, with this contour map in the background. Now remember, we've been thinking of this contour map as representing density of a thin plate of metal, but it doesn't have to represent that. It could represent temperature. Maybe this metal is heated from below, and what we see here is the temperature of the metal. Evidently, you have some sort of heat source right there, where the temperature is higher, and you've had some heat sink there. Actually, this would not necessarily be a realistic temperature distribution because it's not necessarily one of those harmonic functions that came up in the exercises. But we could pretend. So pretend you have a heat source there and a heat sink there, and the temperature everywhere else is given by these level curves. And pretend this is the path of some bug traveling along the sheet of metal. Depending on what units you're talking about, the bug could be, really experiencing some hot temperatures. If that's in degrees Celsius or Fahrenheit. If that's in kelvins, I guess it's cold. Right? Isn't it 273 or so in kelvins? That's like 0 degrees Celsius. Anyway, we don't have to worry about the units. This is some temperature distribution, and the bug is feeling changes in temperature as it walks through the metal. When it's near this region where the values are high because it's shaded more lightly, the temperature is high. The bug is traveling this way, so the temperature gets lower because we're going toward the darker region. Right in there, evidently, because we switch from going toward darker to going toward lighter, probably there's some sort of minimum temperature right around there. Then the temperatures go higher before they get lower again slightly, before they do, it's hard to tell what's going on in there. They ultimately go higher up here. Could I, based on this picture, graph the temperature the bug feels as a function of time? So time goes from -2 to 2. Well, they're positive values, first of all, so the graph is going to be above the horizontal axis. It's going to start high and be decreasing until the bug is right about there. What's the value of t? What's time when you're right about there? I don't know. I have to guess. Based on the form of the equations there, x is t squared minus 1 and y is t cubed minus t, and the fact that I'm going from -2 up to 2 ultimately, I could guess that maybe I'm right about there when t is perhaps -1.5. what's R of negative 1.5? What's the bug's position at that time? 1.25, negative 1.875. 1.25, negative 1.875. Yeah, that's pretty close. I guessed it pretty well. That's the approximate time, I'm sure it's not exact, where it seems like the temperature is reaching a minimum. What is F of R of negative 1.5? Here's an example of where I do need to have the curvy braces at the start. Defining F. When I'm plugging a list into F, you're thinking of the list as being a point. What do I get out? I should get something near 240 or so, a little less. 238.223. Again, I'm not guaranteeing that's a minimum, but it should be close to the minimum. Then the temperature is going to go up as the bug travels from here to right about there. It's going to go up slightly. This is at about negative 1.5 or so. Why did I say right about there? Well, because I'm looking at those level curves and seeing that near this point, they're pointing in this direction. In reality, there would be some level curve that's not actually sketched that would go through this red curve tangent right around there. And that is where you have a local max for the temperature as the bug moves. That makes sense? Because the path is tangent to the level curve at that point. What time is the bug there? Well, the bug is going to be right here when t is 0 by symmetry. So this is still slightly negative time, maybe negative 0.2. Let's see if that's the case. Our negative 0.2. Is it close to that point? Negative 0.96. Positive 0.2. Pretty close. The bug is going to experience a local maximum in the temperature there. It's not going to be much different than the temperature was the other case, but it's going to be slightly bigger, maybe about 240. Yeah, actually bigger than I was expecting, closer to 260. 259.256. So at about t equals negative 0.2 or so, there's going to be a local maximum in the temperature, close to that point. Before the temperature goes down again, it has a local min, probably right about here. Because again, the level curve near this point would be tangent to that curve, maybe right about there, looking at the direction of the nearby ones. What time is the bug there? I'd have to guess that too. Maybe t equals positive 1.2, perhaps. 0.44, 0.5, 0.44. 5. I think I didn't guess so well there. More likely to be 1.3 or 1.4. Seven, 0.9. Does that seem closer? It's certainly closer. I'm not sure if we're quite there yet. Just eyeballing it. That seems to be pretty close when t is 1.4. There it seems like we're going to have some other local minimum. Does it go lower than this one? No, it shouldn't. It should be higher than this one. This one's going to be lower. The temperature here is going to be higher than the temperature here. How could we confirm this? We could make a plot, a regular plot, of f of r of t. There it is. Okay, I can change the plot range to say 0 to 300 to see it on a bigger scale. I think I won't bother. Conceptually, what's going on here, you've got two functions that are being composed. You're plugging R of t into f. R takes real values and gives you points or vectors, two-dimensional points or two-dimensional vectors out. And then f takes those points and gives you a temperature, which is a number back out. When you compose those functions, which you can think of as one of these circle operations, f circle r, that's a regular function that takes real numbers as input and gives you real numbers as output. If you've never seen the circle notation, essentially we're plugging r into f. That's what the circle notation means. Can you see that in the video? Okay. And we might want to know the derivative of this. How is the temperature changing? There's a chain rule for paths that can be used to figure out the derivative of this. It's actually not the easiest way to find the derivative in this case once you've got the formula for this function. However, it's still pretty useful in many cases. If you want to differentiate a function like this, and actually this formula works in higher dimensions too. T needs to be a real number. R of t could be an n-dimensional point or vector. And f then would take an n-dimensional input and give you a real number as output. You take the gradient of f, evaluate it at R of t, and dot that with R prime of t, the velocity vector, like that. And this is analogous to the one-variable chain rule. Take the derivative with respect to x of f of g of x. Pretend you're in calculus 1 right now. What did you learn in calculus 1? You take the derivative of the outside function, f, so you write down f prime. You plug in the inside function into that, and then multiply times the derivative of the inside. It's an analogy here. F is still the outside function, although it's a function of more than one variable. The gradient of f is analogous to the derivative. You're still plugging the inside function into f. Instead of multiplying times the derivative of the inside, you're dotting with the derivative of the inside. The dot product is an analog of multiplication. Let's confirm this with this example. We can confirm it, first of all, by finding a formula for f of r of t. Okay, I need to expand that out. I could use either expand or simplify here before I differentiate. There it is. That's f of r of t. That's the function whose graph looks like this. It's an 8th degree polynomial. What's its derivative? Capital D does the derivative. If I use a percent sign, that's referring to the previous output. Comma D, T differentiates it with respect to T. There we go, there's the derivative. Now let's try checking that this gives us the same thing that the chain rule for paths does right here. Let's go back and look at the formula for f. Let's type in a function that's going to represent the gradient. And I think I want the input as a list. The partial with respect to x, we've seen before, is 3x squared plus y squared minus 10. And the partial with respect to y is 2x times y plus 3. Double check that, make sure I got that right. Yeah, that looks right. That's the gradient. Let's check that if I plug r of t into the gradient and then do the dot product with the velocity vector, then I get the same thing. So I plug R of t into the gradient, do a dot product with the period times r prime of t, simplify it. It is the same thing. Right? So in this case, I mean, if you have the formula for f of r of t, it's easier to just differentiate it that way. But if you've got the gradient and the velocity vector, this might be easier. It depends on what you know as far as which one's easier. What does it mean? Can it be understood in any other way? What does it mean geometrically is what I really mean here. Think about what we've talked about with dot products before. The dot product can be interpreted geometrically by realizing it also is equal to the length of the first vector, the gradient in this case, times the length of the second vector. What did we call the length of that vector before? The speed. That's the velocity vector for the motion. I'll go ahead and write speed. Speed of t. If I put a dot in here, it would represent regular multiplication, not dot product. Dare I do that? Maybe not. This is the length of the gradient vector times the speed times the cosine of the angle between them, which will be a function of t as well, by the way. I just wrote a theta in the last class. I should have written a theta of t. That's going to be a function of t as well. So how is this helpful? Well, let's go back to the visual here, the animation. Let's add in the gradient vector, and the velocity vector for that matter, into this picture. Let me do it on a separate line of code, actually. Put it down here. All right, so how did I do that? I got to use graphics. For example, for the gradient vector, I can do a thick blue arrow. Actually, let's do the velocity vector first. That's a little easier to remember. Although I need to type a formula for the velocity here. Actually, I don't have to do that. I can just type an r prime. Well, let's go ahead and define the velocity vector, v of t to the r prime of t. Conceptually, it'll make it easier to follow this. So I need to start the arrow at the location of the object, the bug, as it moves, r of b. And I need to end the velocity vector arrow, make its tip be at the point whose coordinates can be found by doing r of b plus v of b. So that's going to put the velocity vector into the picture. There it is. Points in the direction of motion, and its length is equal to the speed. Because the bug slows down, it gets shorter and shorter, then the bug speeds up and it gets longer and longer. Let's get the gradient vector in here too. That'll be can be thought as a function of t. Let's see, right here, let's put thick green arrow. Once again, we'll base the gradient vector at r of b. That will make the most sense. So this gradient vector is going to move too. Where should its tip be? R of b plus grad f of r of b. If I plug r of b into that grad f function, that represents the gradient vector. To get the tip of the arrow at the right point, I have to add the position vector for the bug to that. Don't see it yet? That's because it's pointing the opposite direction there initially. Then we see the gradient vector. Okay, it's too long to see it until we get here. That's too long again. I think it's going to get shorter in here, I think. Well, maybe not. Actually, let's go ahead and divide the gradient vector by 5 so we see it better. Let's do the same for the velocity vector. So these are just going to be scaled down versions of both the velocity vector and the gradient vector so we can see them better. There we go. Notice wherever I stop this, say get back here, the gradient vector is perpendicular, orthogonal, normal, all three words can be used, to the level curve at that point. At this point right here, pretend it's right on this level curve. It's perpendicular, orthogonal, or normal, all three words work, to that level curve at that point. It points from dark to light. It's pointing in the direction that f is increasing. It points in the direction of fastest increase, in fact. Look at the angle it makes with the velocity vector. That's bigger than 90 degrees. The cosine of such an angle is going to be negative. These two quantities are positive, making the entire quantity here negative. This derivative is going to be negative at this moment in time, which makes sense if you think about the temperature. The temperature is decreasing, going toward the dark here at that moment in time. Once I reach this spot, that should be where the angle between these two vectors is 90 degrees, because after that point, then the temperature is increasing. Or the gradient vector is, okay, no, it's 90 degrees there, it's not 0. I'm just going to say maybe the gradient vector is 0 there, but we're not at the local midpoint, which is more likely to be in here. 90 degree angle, now the angle is less than 90 degrees. All of these quantities are positive in that case. The bug is experiencing an increase in temperature until I get up toward here. Right there, it's hard to tell, the velocity vector is so short. This picture at least, where we have 90 degree angle again. Then the angle is bigger than 90. Then when we get over here, right about there, now the angle's 90 again. Or right about there. Then the angle's less than 90. How about the magnitudes of these things? Well, if the bug, if the length of the gradient vector stayed constant, which it doesn't do, but pretend it did. If that stayed constant, but the speed was not constant, that would affect the rate of change of the temperature the bug feels. If the bug travels slow, the rate of change of the temperature is going to be small. If the bug travels fast, it's going to be large in absolute value. On the other hand, if you kept the speed constant and varied the length of the gradient vector like we saw, the speed is not constant here, but if we did keep it constant, the length of the gradient vector does affect the rate of change, the temperature that the bug feels. For example, when the level curves are close together, the gradient vector is longer because the graph, the three-dimensional graph, is steeper. So the bug feels a higher rate of change of the temperature. Okay? The bug is traveling on a plane, okay? The graph is just a visual way to represent the function. So the bug's not traveling on the graph, although I suppose you could pretend that, but that's not what I'm pretending. I'm pretending it's traveling in this square that we see. Can I clarify anything there? Question?
When the angle is less than 90 degrees, the temperature is increasing.
When the angle's less than 90 degrees, the cosine of the angle is going to be positive. And assuming these things are positive, this derivative will be positive, so the bug is experiencing a positive rate of change of the temperature with respect to time. In other words, as it moves, it's getting hotter and hotter. It's traveling toward a lighter region. Gradient vectors can be plotted as well with something called vector plot, and it plots a bunch of them at once. To save a little time typing and to show you something, I've shown you this with videos before, but I don't think I've shown this to you in class. Let me copy and paste the code that you see here that's inside of Manipulate, down here. And let me give this code a name. I need an n-squared bracket as well, I see here. Let me give this code a name. Maybe I'll call it curves and gradient of B. What's going on here? What am I doing? I am creating my very own little mathematical function. That's not going to be a regular function in math classes. It's going to be a function that takes a number for input, B, and gives you a graph for output. It's going to be the graph produced by this code at whatever value v you use. Watch, I'll go ahead and use it. Curves and gradient of 1, for example, produces a graph for output, this graph. Curves and gradient of -1 produces a different graph, the picture when b was -1. Looks like that. -1.5 looks like that. So this is a nice way of modularizing your coding to make it more readable, for one thing. I can also put this in a manipulate now. Manipulate curves, and it even saves the name for me. I can just click on that. Curves and gradient of b. B goes from -1.999 to 2, and we get the exact same animation as before. Okay, that's a nice coding trick to realize that you can do that. It makes your code more readable. It makes it easier for you to find the mistakes. Anyway, I'm going to use that to also now add in the vector field plot. I'm going to put a show around this, and also after the comma put vector plot. Vector plot will plot the vector field. Lots of vectors, lots of gradient vectors from the formula for the gradient. So I can put a grad f in here. I don't think I need curly braces around the x and y, but I might be wrong. Let's try it without the curly braces here. So now we're going to see the same picture as before, but with extra vectors in the picture. Or we should have at least. Maybe I do need the curly braces. There we go. I did need the curly braces. Okay. So now you see, again, the same picture, but with a bunch of scaled down gradient vectors for the entire contour map here. They're all, hopefully, the right relative size compared to each other. How much are they scaled down by? I guessed that in the last class period. Let's see if I can guess it for you guys too. Actually, I remember what I guessed. I'm trying to make what I remember match with what this shows here. I'm just going to put it this way. Ah. Keep going the wrong direction. Okay, well, it's off the screen there. If we could see this whole thing, what I was guessing is this little blue arrow is maybe about 1/20th as long as the green arrow. You can't see the entire green arrow here. Since the green arrow was scaled down from the true gradient vector by a factor of 5, if this really is 20 times shorter than the green one, then overall these vectors that you see here are 100 times shorter than they should be. They're scaled down by a factor of 100.